Good afternoon, dear students. So far, we have seen in a case state Boyle's law, Charles' law, Avogadro law, Gay-Lusser law, every laws we have finished. Today, our target is to finish the ideal gas equation and Dalton law and Graham's law. So first, we can start with the ideal gas equation. Ideal gas equation. First of all, you should know what is the ideal gas. The gas which obey in all conditions PV equal to N of T. This is ideal gas equation. The gas which obeys this equation at all conditions, that is called the ideal gas. It is impossible to have such a gases. But there are, we are saying that the gas which obey this equation is called the ideal gas. How the equation is derived? So the property, physical properties of all gases derived by the factors, variables P, V, T and N. These four are governed by the laws, three main laws. What are the laws? Boyle's law, Charles' law and Avogadro's law. Based on these three, by using this variable, we are getting this equation. How the equation is derived? Let us see. What Boyle says: at a constant temperature, volume of gas is inversely proportional to the pressure. This is statement of Boyle. At a constant temperature. At a constant temperature, volume of the gas is inversely proportional to its pressure. In Charles' law, volume of gas is directly proportional to temperature at a constant pressure. Pressure is constant. Avogadro law, volume of gas is directly proportional to number of moles N at a constant temperature and pressure. So these are the statements given by Boyle and Charles and Avogadro that we have seen in last classes. Okay. So by using these three derivation, we can come to the conclusion to get an ideal gas equation. How? So totally what all the three laws says that volume is directly proportional to N and T and inversely proportional to P. Okay. By using these three laws, we can say this: the volume is directly proportional to the N and T and P. You know very well, N is the number of moles, T is the temperature, P is the pressure, and volume. Okay. So the proportionality constant is removed by V equal to N or T by P. See, the R is a gas constant, here proportionality constant. We can say R is a universal gas constant. Then by altering this equation, we are getting that PV equal to N or T. Now we get the equation. PV equal to N or T. So this is the ideal gas equation. How the ideal gas equation is derived? Based on those three laws: Boyle's law, Charles' law, Avogadro law. Boyle's law says that volume is inversely proportional to the pressure. Charles' law says that volume is directly proportional to the temperature. And Avogadro law says that volume is directly proportional to the number of moles. So, based on all these three, volume is directly proportional to the N and T and inversely proportional to the pressure. As when you apply this V equal to N or T, then altering by this PV equal to N or T, this is a ideal gas equation. The gas which obeys this law, PV equal to N or T, in all conditions. Consider in all conditions, that is called ideal. There is no such a gas available. But all are tend to behave as an ideal. All are tend to behave as an ideal. They are trying to behave to ideal. So other gases which are not obeying this rule at all conditions, they are called real gases. What they are called? Real gases. There is a difference between the real and ideal. So all gases can be said as a real gas, but one who obeys this rule, PV equal to nRT, they are called as an ideal gas. So then, from this we can derive the R value. R is a universal gas constant by using this formula PV equal to nRT. If we say R equal to PV by NP, universal gas constant R value. Okay. You know very well what is the atmosphere pressure, volume, and number of moles and temperature. So if we substitute those values, for example, one atmospheric pressure, and the volume is at one atmospheric pressure at 0 degrees Celsius, that means 273 Kelvin. Volume is equal to 22.4. Okay, 22.4 liter. If you substitute those values, you can get a R value. R value may be 0.0821. The units, if you later volume in pressure in atmosphere, volume in decimeter cube, then number of moles per mole, temperature Kelvin. Our other value is there in joule per 8.314 joule per Kelvin. Okay, this is R value. Different type of R value is there for different V. What are the V possibility? V equal to 22.7 is there. At 25 degrees Celsius, if we take 25 degrees Celsius, V equal to 24.5. These are the standard V values are there. If you substituting in this V value, different V value, you will get a different R value. The unit you can need not memorize. You can say pressure is taken. What are the possibility to take pressure units? Atmosphere, bar. These are you can take. Volume, what are the possibility to volume? Volume decimeter cube, liter. Like this you can take. Temperature and number of ME always per mole only. Temperature always you have to take Kelvin. So these are the unit conversion. If you clearly know this formula, you can substitute different standard V values there at a different condition. For 1 atmosphere, 1 bar. And then this is for 25 degrees Celsius, 24. In the condition, by seeing the temperature and pressure, you have to substitute the V value differently. When you differently substitute the V value, you can get a different R value. For the problem, you can the suitable value to be the suitable problem. If data are given in atmosphere, you have to use one R value. If data are given in joules, you have to use that R value differently. Till more calories also there, nearly 1.98 in calories. So round up value R equal to 2. In some cases we can apply. Here if the data are given in calories, you have to use the R is 1.98 or closely 2. So there are different types of R value for different conditions. According to the condition and situation, you have to use the R value. These are about the ideal gas equation. The problem of last of this class, we can see the problems. Now let us move on to the Dalton's law. Then let us move on to Dalton's law. Dalton's law of partial pressure. Partial pressure, let me write a PP. Partial pressure, I cannot write fully. It's not needed. So PP means partial pressure. The short term we have to remember partial pressure PP. TP is total pressure. MF mole fraction. That let me use these terms. You can easily remember. Dalton's law of partial pressure. What is he saying? So it is for a non-reacting gaseous mixture. It is used for the non-reacting gaseous mixture. For example, if you take three gases are there. One gas number 1, gas number 3. 3 gases are inside the container. So if you want the total pressure of this container, simply you cannot say what is the pressure of the container. Dalton is explaining that the pressure of the container is it is a total value of pressure total equal to the partial pressure of gas 1 and the partial pressure of gas 2 and the partial pressure of gas 3. It is nothing but if you assume that 3 gases are inside the container. If there are 3 gases are inside the container total pressure of the container, it is the sum of the partial pressure of the gas 1, gas 2 and gas 3. Okay. This is the Dalton law. Once again I am repeating that Dalton law is nothing but the total pressure of the gaseous mixture can be derived from the sum of the individual pressure of the component present in that gaseous mixture. For example, gas 1, gas 2, gas 3. If you total, there is a non-reacting gases. For example, helium, nitrogen, oxygen, like this non-reacting gases mixture inside into that. We want total pressure of the container. What is the pressure of helium? That is called partial pressure of helium. Plus pressure of nitrogen. Then pressure of oxygen. If you add this, you will get a total pressure of the mixture. Total pressure of the mixture. Okay. So if you substitute the value ideal gases equation, you apply it, you get the derivation here. So total pressure P total equal to partial pressure of P1, P2, P3. Okay, we assume that. And what is the, according to ideal gas equation, PV equal to nRT, then P equal to NV by RT. Okay. If you substitute here and there, P total equal to, substitute this value, P1. So here, volume also constant, temperature also is constant, all already constant. So we need to substitute the number of moles will be varying. So N1 RT by V plus, this is for a P1. What for P2? P2 N2 V RT. So N2 RT plus P3 from the ideal gas equation, if you write N3V RT. Substitute N3 RT by. So these are the constant terms for all. So I am taking is a common N1 plus N2 plus N3 RT by V. Let me write like this, RT by V. Okay. So this is called the N total number of moles, N total RT by V, So the simplest way to calculate the partial pressure is nothing but the partial pressure of individual component. Partial pressure, that is equal to total pressure into mole fraction. Total pressure into mole fraction. Okay. If you want the partial pressure of this one, you can get this total pressure into mole fraction. This is way, the total pressure into mole fraction. How the formula comes? Partial pressure P equal to total pressure into mole fraction. So from this we can take a P total equal to N total by RT, N total into RT by V. So instead of the RT by V, we can substitute what? That is from the PV equal to nRT. Okay. So P equal to P by N equal to RT by V. Okay. For ith gas, PA equal to PI by N equal to NA equal to RT by V. So the term of RT by V we can substitute as PI by N. So total pressure, that is equal to N total into RT by V. Instead of RT by V, I am substituting PI by Ni. Okay. So PI equal to partial pressure of individual gas, ith gas or individual gas. So if we need PI, total pressure total into Ni by N total, that is equal to PI. Now you got this is formula. Partial pressure equal to total pressure into mole fraction. How the formula comes here? This is way. This is the way how the formula comes here. PI is a partial pressure of ith gas, individual gas. If we take total pressure into Ni by N total. What is this Ni by N total? Number of moles of individual Ni, number of moles of individual gas by total number of moles of gases present in the mixture. For example, N total equal to N1 plus N2 plus N3. So by using this, if we want a partial pressure of gas number 1, partial pressure of gas number 1, partial pressure PP of gas number 1. Or example, we take for the mixture contains nitrogen and helium and argon. Like these three gases are there now. If you assume that partial pressure of nitrogen equal to, that is equal to number of moles of nitrogen divided by total number of moles mean number of moles of nitrogen plus number of moles of helium plus number of moles of argon into P total pressure. Likewise, if you write for partial pressure of helium mean, here you change N number of helium divided by number of nitrogen plus number of helium plus number of argon. Okay. Number of argon, N is small. Number of helium, number of argon. You have to write like this. Into P total. That's why I simplified the formula. I have given this. We want partial pressure. For problem, if you elaboratedly, you know that how the formula comes. Partial pressure equal to total pressure into mole fraction. What is the mole fraction? Mole fraction equal to number of moles of individual divided by total number of moles. Total number of moles in the mixture. The gas is mixture, this is called a total number of moles, mole fraction. So these are the elaborated form of the Dalton's law. Simply what Dalton says that Dalton says nothing but the total pressure of any gaseous mixture, non-reacting gaseous mixture can be calculated by the individual partial pressure of the component gases present in it. For P total equal to P1, P2, P3. The sum of the values. Okay. Then let us move on to the Graham's law. Okay. Graham's law is nothing but first if a container having the mixture of gases, they consider to A and B. Two gases are present in that container. What is the tendency of gases? To flow from the more concentration to less concentration. Among these, which one is the more concentration or less concentration? The tendency of gas get into the another gas. This is called direction. Okay. So this is called diffusion. So Graham's law of diffusion. Diffusion is nothing but when a gas is diffused through the other gas, moving towards the other gas. This movement is called a diffusion. One gas is moved towards the others. Where they move high concentration, the gas which having high concentration is moving towards the gas having the low concentration. This process is called a diffusion. Then the container having a mixture of gases, they come out from the small hole. Mixture of gases coming out from the small hole. So that is called a effusion. That is called effusion. This is diffusion. The Graham's laws of diffusion, how fast, the rate, how much fast the gas is moving to that other into the other gas, or how fast it will effuse through the small hole. The mixture of gas is present. The mixture is which gas is coming out first, how much fast this gas coming out first, how much fast that A, B, like this. This is effusion. So, Graham's come to the conclusion that he is saying that the rate of effusion or diffusion, rate of effusion or diffusion is inversely proportional to the square root of that molecular mass. Is that law? The rate of effusion or rate of diffusion inversely proportional to the square root of the molecular mass of that particular gas. It can be written gas A, gas B, rate of gas A, rate of gas B equal to, then it can be written as square root of MB, molecular mass of B by molecular mass of A. This is the way we can write molecular mass of A by molecular mass of B. Then at a different pressure, rate of A and B that is equal to different pressure mean pressure of A by pressure of B. Then okay, this is Graham's law of effusion and diffusion. Once again I am saying the diffusion. What do you mean by diffusion? Diffusion means the mixture contains many number of gases. We consider two gases are there in the mixture. One of the gases tend to get into the other. That is a high concentrated gas is moving towards into the lower concentration, because tendency of gas is it is moved from the higher concentration to lower concentration. The movement is called diffusion. This movement is called getting into other gas. This is called diffusion. If the same mixture is coming out from the small hole that is called effusion. Okay, first of all you should know what is the diffusion and the effusion. What is the Graham's law actually? Actually Graham's law says that rate of diffusion or rate of effusion, whatever may be, both rate of effusion or rate of diffusion is inversely proportional to the square root of molecular mass of that particular gas. When the two gases are comparatively taken, the gas A and gas B, if you take the rate of A by rate of B equal to square root of molecular mass of B by A. Then rate of A by rate of B is this form of a different pressure. And if you take pressure a different pressure, then you can have a PA by PB, that is square root of MB by MA. This is Graham's law. Okay, now it's clear. What is the Graham's law? Graham's law is nothing but a rate of effusion or rate of diffusion is inversely proportional to the square root of the molecular mass of the particular gas. Okay. Now let us do some problems for the both all these three laws: ideal gas equation and Dalton law and Graham's law. Let us do that problem. Then we can wait at the class. Let us see example problem for the ideal gas. Okay. So given I have written the not a complete problem, I have just written the data alone. The number of moles 2 moles, volume 6 decimeter cube, temperature 70 degrees Celsius. What is the pressure? What is the ideal gas equation? PV equal to nRT. Okay. So what are the data are given? N is there, or gas constant that we need to apply. Already we know temperature. Temperature always should be taken in a Kelvin. So clear the solution first. Temperature is in Celsius, just you change it. 70 plus 273 Kelvin. Okay, that is the temperature. Then nothing else to need to change. So just apply what is called pressure is asked. Pressure equal to N. N equal to number of moles already is given. So 2 R equal to gas a decimeter cube. So you can 0.821 R value gas constant. Then temperature 70 degree Celsius We need to convert into Kelvin. 70 plus 273 Kelvin. Okay. Divided by, so P equal to nRT by B. So B, volume 6 dc. If you do and simplify all those, you may get a 9.39 atmosphere. This is the solution how we are getting for the ideal gases. So in the problem, they may give volume, number of moles and temperature. You need to find the pressure or anything else interchanged. Always in the gaseous state problem, you consider the temperature. Temperature should be in Kelvin. They mostly all the problem they will give in Celsius. You convert wherever you find the temperature in Celsius, you convert into Kelvin, then do the problem. Otherwise, you may go wrong. Okay. Then the Dalton's law problem. See, Dalton's law is just I want to recall you that Dalton's law is nothing but a total pressure. Okay. Total pressure that is equal to sum of the partial pressure of the individual gases in the mixture. Okay. See, a number of moles is provided to you. They are asking what is the mole fraction. What are the question mole fraction you need to find. Then a partial pressure of individual gas. Just they are given a data. There will be total pressure value will be there. Total pressure may be there. The total pressure of this mixture will be 2. You imagine that 2. If you imagine that it is 2, you have to work out this problem completely. Okay. So by using the number of moles, so we are going to find out the first mole fraction. Mole fraction of that is X. Mole fraction of Ne. Mole fraction of Ne means number of moles of Ne neon divided by number of moles of Ne, total number of moles. That is the formula, no? Mole fraction. Number of moles divided by total number of moles. That is mole fraction. Number of moles of neon, number of moles of argon plus number of moles of xenon. So number of moles of neon, argon, xenon is a question itself they are given. If you apply it, you may get an answer. 0.76 divided by 4.76 plus 0.74 into 2.5. If you add and you can get that value like this 0.595. That is a mole fraction of neon. Like this individually you need to calculate for all those two. Again, that is not a question. Mole fraction they didn't ask. The question is that find out the partial pressure of individual gas. Let me find the by using mole fraction I can calculate the partial pressure of neon. Neon, I have a mole fraction of neon. Then by using the mole fraction of neon and the total pressure I am taking is 2, then I can calculate the partial pressure. If I do the problem, what is the formula? Partial pressure that is equal to mole fraction into total pressure. This is the formula you have to always keep in mind. So individually, I am doing for one, you do in the home remaining things. For neon, if I take the neon, what is the partial pressure of neon? I am going to partial pressure of neon, that is I am going to calculate. Mole fraction just now I have calculated, that is 0.595. Okay. Plus total pressure into total pressure already given in a question paper itself, that is 2. If you add this, you may find that answer partial pressure of neon 1.19. Okay, 1.19. Likewise, if you do the problem for argon, if you do mole fraction of argon, you have to find out first. Then you put it in the formula, you can get a partial pressure of argon. Likewise, if you put find the mole fraction of xenon first, then you put substitute in the formula, you can get the partial pressure of xenon. The final answer may be you will get like this. Okay, this is the problem for Dalton's law. Then let us move on to the Graham's law. Graham's law, what is saying? Graham's law, according to Graham's law, the rate of effusion or diffusion is inversely proportional to the molecular mass of that particular case. So comparing the two cases, what is there? Here they have taken the question is like this. The unknown gas has the power rate of 0.5 times 0.5 of nitrogen. So they didn't give a nitrogen, but we assume that 1. So what is the formula? Rate of nitrogen, rate of unknown, if you take it, rate of unknown by rate of nitrogen, that is equal to molecular mass of nitrogen divided by molecular mass of unknown. Okay. What is the question? What is the molecular mass of unknown? This is a question in your book. We want molecular mass of unknown. Rate of unknown is 0.5. Rate of nitrogen, if you assume that 1, because they are given like this only. If you take 1, then root of molecular mass of nitrogen, you know that is 28. Then molecular mass of unknown, that is we need to find molecular mass of unknown, we need to find. Okay. What to do? If you take square of these two, the square root will be cancelled. So I am taking square of these two. For in order to cancel this, 0.5 square equal to 28 by molecular mass unknown. Like this it will come. Then we want molecular mass of unknown, that is equal to 28 by 0.5 square or 0.5. If you simplify this, you will get the answer. That's all. This is the way how you have to calculate many problems, many questions, as well as state board onwards, many questions you may find this in the Graham's law like this. Okay. That's all about this, the Graham's law problem. So today we have seen that what is the ideal case, what is the ideal case equation, what is the Dalton law, what is the formula. From Dalton law what we can get. One more thing, and the application of Dalton law is nothing but the downward pressure gases, the collected, it can be, so if your gas is mixed in water, the pressure, total pressure, if gas is mixed in the water, the total pressure will be pressure of dry gas, that is equal to pressure of the gas, pressure of the mixture minus pressure of the water vapor, water vapor. This is nothing but a aqueous tension. Okay. So total pressure minus water vapor. You need to subtract the water vapor to get the pressure of the dry gas. Okay. The Dalton law over the Graham's law, you can calculate like this. There are a lot of exam problems are there in your book. You may find it. Thank you. Tomorrow we will see.